Welcome to this peaceful journey through the fascinating world of semiconductor chips. As you settle in and let your mind drift, allow these gentle facts to wash over you like soft waves, carrying you toward restful sleep. The story of semiconductor chips begins with something quite ordinary, something you might find beneath your feet on a sunny beach day. Silicon, the foundation of nearly every computer chip ever made, comes from sand. Not just any sand, but a special type called silica sand, which contains high concentrations of silicon dioxide. Silicon is the second most abundant element in the Earth's crust, making up about 25% of its mass, exceeded only by oxygen. This means the basic ingredient for the technology that powers our modern world is quite literally all around us. To transform ordinary sand into the ultrapure silicon needed for computer chips, manufacturers must heat it with carbon in an electric arc furnace at temperatures exceeding 2,000 degrees Celsius. At these extreme temperatures, the carbon reacts with the oxygen in the silicon dioxide, releasing carbon dioxide gas and leaving behind pure silicon. But this silicon is not yet pure enough for making chips. It must be refined again and again until it reaches a purity level of 99.9999999%. Meaning there can be only one foreign atom for every 10 billion silicon atoms. Once the silicon reaches this extraordinary level of purity, it is melted and formed into large cylindrical ingots. These ingots are grown using a process called the Czochralski method, where a small seed crystal is dipped into molten silicon and slowly pulled upward while rotating. As the seed rises, silicon atoms attach themselves to its surface in perfect alignment, creating a single continuous crystal that can weigh around 100 kilograms and measure 300 millimeters in diameter. This process must be performed with extreme precision because even the slightest imperfection in the crystal structure can ruin the chips that will eventually be made from it. The cylindrical silicon ingots are then sliced into thin wafers using a wire saw that works somewhat like an egg slicer. These wafers are cut incredibly thin, measuring less than 1 millimeter in thickness. After slicing, each wafer undergoes extensive polishing until its surface is atomically smooth, like a perfect mirror. The smoothness required is almost beyond comprehension. If a silicon wafer were scaled up to the size of a football field, the largest imperfection on its surface would be smaller than the thickness of a blade of grass. The history of semiconductors stretches back further than many people realize. In 1782, Alessandro Volta became the first person to use the term semiconducting to describe the electrical properties of certain materials. Half a century later, in 1833, Michael Faraday observed that the resistance of silver sulfide decreased as temperature increased, which was the opposite of how metals behaved. This curious observation would eventually lead to our understanding of how semiconductors work. The first practical application of semiconductor technology came in 1874, when Carl Ferdinand Braun discovered rectification in metal sulfides. He found that when he touched a metal point to certain crystals, electrical current could flow in one direction much more easily than the other. This discovery would later prove essential for radio and radar systems. The transistor, perhaps the most important invention of the 20th century, was officially demonstrated on December 23, 1947, at Bell Laboratories in New Jersey. Three scientists, William Shockley, John Bardeen, and Walter Brattain, showed that their device could amplify electrical signals. However, the concept of a field effect transistor had actually been patented much earlier, in 1925, by Julius Lilienfeld. Shockley, Bardeen, and Brattain did not invent the transistor so much as they discovered how to make it work practically. Before transistors, electronic devices relied on vacuum tubes. These glass tubes were large, generated tremendous heat, consumed enormous amounts of power, and burned out frequently. The first general-purpose electronic computer, ENIAC, used approximately 18,000 vacuum tubes and weighed about 30 tons. It filled an entire room and required constant maintenance as tubes failed. The invention of the transistor changed everything, making electronic devices smaller, cooler, more reliable, and far more efficient. In 1954, Morris Tannenbaum at Bell Labs created the first silicon transistor using a technique called the grown junction method. Later that same year, Gordon Teal at Texas Instruments independently developed the first commercial silicon transistor. Silicon was chosen over germanium, which had been used in earlier transistors because of its abundance and low cost. Though germanium actually has better electrical properties in some ways, silicon's stability and availability made it the material of choice for the growing electronics industry. The integrated circuit, which combines multiple transistors and other components on a single chip, was invented independently by two people in 1958 and 1959. Jack Kilby at Texas Instruments created the first working integrated circuit using germanium. Robert Noyce at Fairchild Semiconductor developed the first practical silicon integrated circuit using what was called the planar process. This approach proved more suitable for mass production and became the foundation for all modern chip manufacturing. The Intel 4004, released on November 15, 1971, was the first commercially available microprocessor. This revolutionary chip contained 2,300 transistors on a piece of silicon measuring just 12 square millimeters. It was priced at $60, which would be equivalent to about $466 today. The 4004 could perform 60,000 operations per second, which seemed incredibly fast at the time. The engineers who designed it, Ted Hoff, Federico Faggin, and Stanley Mazur, along with Masatoshi Shima from the Japanese calculator company Busicom, could hardly have imagined what their invention would lead to. The development of the Intel 4004 began as a contract to build calculator chips for Busicom. The original plan called for 12 custom chips, but Ted Hoff realized this approach was too complex. Instead, he proposed creating a general-purpose processor that could be programmed to perform different tasks. This brilliant insight transformed what would have been a specialized calculator chip into the first true microprocessor, a tiny computer brain that could be programmed to do almost anything. Interestingly, Busicom was not particularly excited about the 4004. By the time it was completed, the calculator market had collapsed, and they wanted to renegotiate the price. Intel seized this opportunity, offering to reduce the chip's cost in exchange for getting back the rights to sell it for non-calculator applications. Busicom agreed, not realizing they were giving away one of the most important inventions in history. Busicom eventually went bankrupt in 1974, while Intel went on to become one of the most valuable companies in the world. Gordon Moore, one of Intel's co-founders, made an observation in 1965 that would become one of the most famous predictions in technology. He noticed that the number of transistors on an integrated circuit had been doubling roughly every year, and he predicted this trend would continue. In 1975, he revised his estimate to doubling every 2 years. This observation, known as Moore's Law, has proven remarkably accurate for more than 50 years, though the pace has slowed somewhat in recent years. To understand the scale of progress driven by Moore's Law, consider this. The first Intel processor in 1971 contained 2,300 transistors. By the early 2000s, processors contained hundreds of millions. Today's most advanced chips contain tens of billions of transistors. Apple's M1 Max chip, for example, contains 114 billion transistors. The GPU with the highest transistor count as of 2024 is NVIDIA's Blackwell-based B100 accelerator, which contains 208 billion transistors. The average smartphone processor today contains around 10 to 20 billion transistors, more computing power than existed in the entire world just a few decades ago. The shrinking of transistors is measured in nanometers, which are billionths of a meter. To put this in perspective, a human hair is approximately 100,000 nanometers wide. A strand of human DNA is about 2.5 nanometers across. The most advanced chips being manufactured today use processes measured at just 3 nanometers. At this scale, transistor features are only about 10 silicon atoms across. A silicon atom itself measures just 0.2 nanometers in diameter. Scientists have pushed transistors to their absolute limits. In 2022, researchers in China created a transistor with a gate length of just 0.34 nanometers, the thickness of a single layer of carbon atoms. This is essentially the smallest a transistor gate can possibly be. Below about 5 nanometers, quantum effects like electron tunneling make it increasingly difficult to control the flow of electricity through silicon transistors. Electrons begin to simply pass through barriers that should stop them, like ghosts walking through walls. Manufacturing these incredibly small transistors requires extraordinary precision. The primary tool for creating chip patterns is called photolithography, which uses light to transfer circuit designs onto silicon wafers. For decades, the industry used deep ultraviolet light with a wavelength of 193 nanometers. But as transistors shrank below about 45 nanometers, this light was no longer precise enough to create the tiny features required. The solution was extreme ultraviolet lithography, or EUV, which uses light with a wavelength of just 13.5 nanometers. This is about 14 times shorter than the previous generation of lithography light. EUV light does not occur naturally on Earth and must be generated in a remarkable way. Tiny droplets of molten tin are fired through a vacuum at millions of droplets per second. A powerful laser hits each droplet twice, first flattening it into a pancake shape, then vaporizing it to create a plasma that emits EUV light. This process happens 50,000 times every second. Only one company in the world makes the machines capable of EUV lithography. ASML, a Dutch company headquartered in Veldhoven in the Netherlands, has a complete monopoly on this critical technology. Each EUV machine costs between $150 million and $400 million. They weigh around 180 tons and consume more than 1 megawatt of electrical power. Shipping just one machine requires 3 jumbo jets. Each machine contains more than 100,000 components, including mirrors that are so precisely manufactured that if they were scaled to the size of Germany, their imperfections would be smaller than 1 millimeter. ASML invested more than 6 billion euros over 17 years developing EUV technology. The company acquired Cymer, a specialist in light sources, to help solve the tremendous technical challenges. Intel, Samsung, and TSMC together invested $6 billion in ASML in 2012 to help fund the completion of EUV development. The first prototype EUV machine in 2006 could process just one wafer in 23 hours. Modern EUV machines can process over 200 wafers per hour. The mirrors inside EUV machines, manufactured by the German company Zeiss, are described as the most precise mirrors in the world. They are made by identifying tiny imperfections on their surfaces and then knocking off individual molecules using techniques like ion beam figuring. The precision required is almost incomprehensible. Light must bounce off multiple mirrors inside the machine, and any imperfection would scatter the light and ruin the incredibly fine patterns being created. The manufacturing of semiconductor chips takes place in facilities called fabrication plants, or fabs. These are among the most expensive structures ever built. TSMC's latest fab, capable of manufacturing 3-nanometer chips, cost $19.5 billion to construct. A single modern fab can cost anywhere from $10 to $30 billion, depending on the technology level. Intel's planned expansion in Arizona, Ohio, and elsewhere involves investments of tens of billions of dollars. Inside a fab, the air must be kept extraordinarily clean. Semiconductor cleanrooms are classified by how many particles they allow per cubic meter of air. The most advanced fabs operate at ISO class 4 or 5, meaning they allow only 352 to 35,000 particles per cubic meter at the 0.5 micrometer size. By comparison, the outside air in a typical city might contain 35 million particles per cubic meter. A fab's cleanroom is about 100,000 times cleaner than a hospital operating room. To maintain this level of cleanliness, workers in semiconductor fabs wear special garments called bunny suits. These coveralls, along with hoods, booties, masks, and gloves, prevent human skin cells, hair, and other particles from contaminating the chips. Workers pass through air showers that blow HEPA-filtered air over their suits to remove any particles that might be clinging to them. Even the tiny particles that humans naturally shed from their skin could destroy chips worth hundreds or thousands of dollars. The temperature and humidity inside a cleanroom must be precisely controlled. Typical semiconductor cleanrooms maintain temperatures of 20 degrees Celsius plus or minus 1 degree. relative humidity is kept between 30 and 50%. These conditions are maintained 24 hours a day, 7 days a week, 365 days a year. The HVAC systems required for this level of control are among the most sophisticated in any industry. Water plays a crucial role in semiconductor manufacturing, and the quantities required are staggering. A large semiconductor fab can consume up to 38 million liters of water per day, equivalent to the daily water consumption of about 300,000 people. Globally, the semiconductor industry consumes as much water as Hong Kong, a city of 7.5 million people. Most of this water is used to rinse silicon wafers during the fabrication process. The water used in chip manufacturing must be ultra-pure, thousands of times cleaner than drinking water. It goes through multiple stages of treatment, including reverse osmosis, deionization, and ultrafiltration to remove minerals, particles, bacteria, dissolved gases, and other contaminants. Even the tiniest impurity in the rinse water could leave residue on a chip that would cause it to fail. Producing ultra-pure water is itself an energy-intensive process that contributes significantly to a fab's overall resource consumption. Semiconductor manufacturing also requires enormous amounts of electricity. Large fabs can use 30 to 50 megawatts of peak electrical capacity, enough to power a small city. Some facilities consume over 100 megawatt-hours of power hourly, more than oil refineries or automotive plants. The total energy consumption of the semiconductor industry in 2021 was approximately 149 billion kilowatt-hours, equivalent to the electricity consumption of a medium-sized country. The process of manufacturing a single chip involves hundreds of individual steps and can take 2 to 3 months to complete. The silicon wafer is coated, etched, doped, and layered dozens of times. Modern chips may have over 30 layers of circuits stacked on top of each other, creating intricate three-dimensional structures. If you could magnify a chip and look at it from the side, you would see something like a miniature multi-level city, with highways of metal connecting billions of tiny transistors. Despite all this precision and care, not every chip that comes off the production line works correctly. The percentage of functioning chips from a batch, called the yield, is a critical measure of a fab's efficiency. A good yield is 90% or higher, meaning about 1 in 10 chips must be discarded or downgraded. For cutting-edge processes, yields can be much lower, especially when production is first ramping up. Even a tiny speck of dust that lands on a wafer at the wrong moment can destroy dozens of chips. Once the circuits are complete, the wafer is cut into individual chips called dies. A single 300mm wafer might produce hundreds or even thousands of dies, depending on the chip size. Each die is then tested individually to verify it works correctly. Dies that pass all tests are packaged, a process that involves mounting the delicate silicon chip on a substrate, connecting it to external pins or bumps, and encasing it in a protective shell. The packaged chip is then tested again before being shipped to customers. The chips inside your smartphone are among the most complex objects ever created by humans. A modern smartphone contains at least 10 to 20 billion transistors in its main processor alone. If you counted all the transistors in all the chips on a phone's circuit board, including memory, communications, and power management chips, the total could exceed 20 to 30 billion. Each of these transistors switches on and off billions of times per second, working in perfect coordination to run your apps, display your photos, and connect you to the world. To appreciate how far we have come, consider that the computer that guided the Apollo 11 mission to the moon in 1969 had just 32,768 bits of RAM and 589,824 bits of ROM. It was about twice as powerful as a Nintendo gaming console from the 1980s. A modern smartphone has approximately 100,000 times more processing power than that Apollo guidance computer, with about 1 million times more RAM and 7 million times more ROM. The device in your pocket is more powerful than all the computers that existed on Earth when humans first walked on the moon. The materials required to make semiconductor chips come from all over the world, and some are quite rare. While silicon itself is abundant, the manufacturing process requires many other elements. gallium and germanium are particularly important for certain types of chips. China accounts for about 98% of global raw gallium production and 67% of raw germanium production. These materials are essential for high-speed communications chips, radar systems, and solar cells. Rare earth elements also play important roles in semiconductor manufacturing. These 17 metallic elements, with names like cerium, europium, gadolinium, and neodymium, are used to dope other materials and improve chip performance. China controls about 60% of the world's rare earth supply and has an even larger share of the refining capacity. This concentration of critical materials in one country has become a significant geopolitical concern. The semiconductor industry contributes to greenhouse gas emissions in ways that might surprise you. Some of the gases used in chip manufacturing, like sulfur hexafluoride and perfluorocarbons, are extremely potent greenhouse gases, thousands of times more powerful than carbon dioxide at trapping heat. The industry has made progress in reducing these emissions, but the challenge grows as chip production increases to meet ever-growing demand. Taiwan has become extraordinarily important to the global semiconductor industry. Taiwan Semiconductor Manufacturing Company, or TSMC, is the world's largest contract chip manufacturer, producing chips for companies like Apple, AMD, NVIDIA, and many others. TSMC and Samsung in South Korea are the only companies capable of manufacturing the most advanced chips. This concentration of cutting-edge manufacturing in East Asia, particularly on an island that exists in a complex geopolitical situation, has raised concerns about supply chain vulnerability. The foundry model that TSMC pioneered has transformed the semiconductor industry. Before TSMC was founded in 1987, companies that wanted chips generally had to design and manufacture them themselves. TSMC's founder, Morris Chang, created a new business model where one company could specialize entirely in manufacturing while other companies focused on design. This allowed fabless semiconductor companies to emerge, firms that design chips but own no factories. Today, some of the most valuable chip companies, including NVIDIA and AMD, are fabless. Designing a modern chip is a monumental undertaking that can take years and cost hundreds of millions of dollars. Teams of hundreds or thousands of engineers work to specify what the chip should do, design its architecture, create the circuit layouts, verify that everything works correctly through extensive simulation, and prepare the design for manufacturing. A single error in a chip design can cost millions of dollars to fix because new masks must be created and new wafers fabricated. The design of a chip must account for countless physical effects that become increasingly significant at tiny scales. Heat dissipation is a constant concern because billions of transistors switching billions of times per second generate tremendous heat in a very small area. In terms of power density, a modern processor chip is comparable to a nuclear reactor. If the heat is not removed efficiently, the chip will slow down to protect itself or, in extreme cases, be damaged permanently. One innovation that helped continue Moore's Law progress was the FinFET transistor, introduced commercially by Intel in 2011. Traditional transistors were essentially flat, two-dimensional structures. FinFETs have a three-dimensional design where the conducting channel rises up from the surface like a fin. This allows the gate to wrap around the channel on three sides, giving much better control over the flow of electrons. FinFETs enabled chips to continue shrinking while maintaining good electrical characteristics. The next major transistor design is the gate-all-around transistor, sometimes called a nanosheet or ribbon FET. In this design, the gate completely surrounds the conducting channel, providing even better control than FinFETs. Samsung began mass production of gate-all-around transistors in 2022, and other manufacturers are following. This design is expected to enable continued transistor scaling for several more generations. As traditional scaling becomes increasingly difficult, chip designers have found other ways to improve performance. One approach is advanced packaging, which involves stacking multiple chip dies on top of each other or placing them side by side in the same package. This allows designers to mix and match different types of chips, combining high-performance logic with memory or specialized accelerators in configurations that would be impossible with a single chip. Another innovation is the chiplet architecture, where a single processor package contains multiple smaller chips that work together. Instead of trying to manufacture one enormous chip with very low yield, manufacturers can build smaller chiplets with higher yields and combine them. AMD's Ryzen processors and Intel's latest designs use this approach. It represents a significant shift in how chips are designed and manufactured. Artificial intelligence has become both a major driver of semiconductor demand and a tool for designing better chips. Training large AI models requires enormous computing power, driving demand for specialized chips like NVIDIA's GPUs. At the same time, AI is being used to help design chips themselves, automating tasks that once required extensive human effort. Some companies are using AI to optimize chip layouts, predict manufacturing defects, and improve performance. The development of quantum computers represents a potential revolution in computing, though practical quantum computers that outperform classical ones for useful tasks remain largely in the future. Unlike classical transistors that can be either on or off, quantum bits or qubits can exist in superpositions of both states simultaneously. This property, along with quantum entanglement, could enable certain calculations to be performed exponentially faster than on any classical computer. The economic importance of semiconductors can hardly be overstated. The global semiconductor industry reached $555.9 billion in revenue in 2021 and is projected to grow substantially in coming years. Some forecasts suggest the industry could reach $1 trillion by 2030, driven by demand for AI chips, electric vehicles, data centers, and the Internet of Things. Chips are in virtually every electronic device we use, from our phones and computers to our cars, appliances, and medical equipment. Semiconductors have enabled medical advances that were once in the realm of science fiction. Pacemakers, cochlear implants, and insulin pumps all rely on semiconductor chips. Researchers are developing chips that can be implanted in the brain to help paralyzed patients control prosthetic limbs or communicate through thoughts. Some people have voluntarily implanted small RFID chips in their hands for convenience, using them to unlock doors, start cars, or make payments. The first FDA-approved human microchip implant came in 2004. Called VeriChip, it was about the size of a grain of rice and could store a 16-digit identification number. While VeriChip is no longer sold, the technology has continued to develop. In Sweden, thousands of people have received chip implants, using them for everything from storing medical records to boarding trains. The chips typically operate using radio frequency identification technology and do not require batteries. Looking to the future, researchers are exploring many alternatives to traditional silicon transistors. Carbon nanotubes, which are tiny cylinders of carbon atoms, have excellent electrical properties and could potentially enable faster, more efficient transistors. Graphene, a single layer of carbon atoms arranged in a honeycomb pattern, is the strongest material ever discovered and has unique electrical properties. Scientists have created transistors using these materials in laboratories, though bringing them to mass production remains challenging. The concept of neuromorphic computing aims to create chips that work more like the human brain. Traditional computers process information sequentially, moving data between memory and processor. The brain processes information in parallel, with memory and processing integrated together. Neuromorphic chips attempt to mimic this architecture, potentially enabling more efficient processing of pattern recognition and other tasks at which brains excel. Photonic computing uses light instead of electricity to perform calculations. Photons can travel faster than electrons and generate less heat, potentially enabling faster, more efficient computers. Researchers have made significant progress in integrating photonic components with traditional electronic circuits. While fully photonic computers remain far in the future, hybrid systems that use light for certain tasks are already being developed. The relationship between humans and semiconductor technology continues to deepen. Every year, more aspects of our lives depend on these tiny slivers of silicon. The cars we drive contain thousands of chips controlling everything from the engine to the infotainment system. Our homes are filled with smart devices, from thermostats to refrigerators, all powered by semiconductors. The infrastructure of modern society, from power grids to communication networks to financial systems, runs on chips. Despite all this complexity, there is something almost poetic about the journey of a semiconductor chip. It begins as sand, one of the most common substances on Earth, gathered from special quarries where the silicon dioxide content is highest. Through processes involving temperatures hotter than volcanic lava, chemicals more corrosive than anything found in nature, and precision finer than any human hand could achieve, this sand is transformed into crystals of almost perfect purity. These crystals are sliced, polished, and patterned with circuits smaller than a virus, creating machines that can perform billions of calculations every second. The people who make this possible number in the millions worldwide. There are the scientists who discover new physical phenomena and the engineers who figure out how to apply them. There are the technicians who operate the fabs 24 hours a day, and the designers who spend years perfecting each new chip. There are the miners who extract the raw materials and the logistics experts who move components around the globe. The semiconductor industry represents one of the most complex and coordinated human endeavors ever undertaken. As you drift towards sleep, consider that the device playing this recording contains more computing power than all the computers that existed when your grandparents were young. The tiny chips inside it represent the culmination of centuries of scientific discovery, decades of engineering development, and billions of dollars of investment. They connect you to billions of other people around the world, give you access to essentially all human knowledge, and perform feats that would have seemed like magic just a few generations ago. And yet, all of this extraordinary technology ultimately traces back to sand. The most common ingredient of beaches and deserts has become the foundation of our digital age. Through human ingenuity and persistence, we have learned to arrange atoms with incredible precision, to control electrons flowing through channels narrower than strands of DNA, and to create machines of almost unfathomable complexity from one of Earth's most abundant resources. The next time you use your phone, your computer, or any other electronic device, you might take a moment to appreciate the remarkable journey those chips have taken. From sand dunes to silicon ingots, from wafer fabs to your fingertips, semiconductor chips represent one of humanity's greatest achievements. They are tiny mirrors reflecting our curiosity, our creativity, and our endless drive to understand and reshape the world around us. The transistor count in chips has grown from 2,300 in 1971 to over 200 billion today, an increase of nearly 100 million times in just over 50 years. This exponential growth has enabled advances in medicine, communication, transportation, entertainment, and virtually every other field of human endeavor. It has changed how we work, how we play, how we learn, and how we connect with each other. Moore's law may eventually reach its limits as transistors approach atomic scales, but human ingenuity shows no signs of slowing. New materials, new architectures, new manufacturing techniques, and entirely new approaches to computing continue to emerge. The next 50 years of semiconductor development may be even more transformative than the last 50, taking us to places we cannot yet imagine. For now, though, let these thoughts of silicon and circuitry, of transistors and photons, of human achievement and natural abundance carry you gently toward sleep. The chips in your devices will continue their tireless work, performing billions of calculations every second while you rest. Tomorrow, the technology will still be there, waiting to serve you, a testament to what we can achieve when we combine scientific understanding with engineering skill and determined effort. The world of semiconductors is vast and deep, filled with wonders that most people never see or think about. From the quantum effects that govern electron flow at nanometer scales to the global supply chains that move materials across continents, from the billion-dollar factories that run around the clock to the devices that fit in your pocket, it is a world of extremes. The smallest human-made structures and the largest industrial investments, the purest materials and the most complex systems, the most ancient natural resources and the most advanced technologies. As sleep approaches, Let your mind rest easy knowing that this remarkable technology continues to improve, continues to enable new possibilities, continues to connect us and empower us in ways large and small. The chips will keep working through the night, just as they have every night since the first microprocessor came to life more than half a century ago. And tomorrow, when you wake, they will be ready to help you face a new day, these tiny marvels of engineering that began their journey as grains of sand. The history of semiconductors is really the history of human curiosity and determination. From Volta's first observations in 1782 to today's 3-nanometer chips, every advance has built upon the work of those who came before. Thousands of scientists and engineers, working across generations and around the world, have contributed to this collective achievement. Their work touches your life every day, in ways both obvious and hidden. Think of the chips that monitor your heart if you wear a fitness tracker. Think of the chips that control the brakes in your car, reacting faster than any human driver could. Think of the chips that route your phone calls, process your photos, and keep the power grid running. Think of the chips in hospitals that help doctors diagnose diseases, and the chips in satellites that help farmers grow food. All of these chips share that same fundamental heritage, that same journey from sand to silicon to circuit. The journey continues even now, as researchers work on problems that have not yet been solved, and engineers build factories that have not yet been imagined. Somewhere in the world, at this very moment, someone is studying a new material that might replace silicon. Someone else is designing a chip that will be more powerful than anything that exists today. Someone is discovering a new way to arrange atoms, a new way to control electrons, a new way to transform energy into information. This is the story of semiconductors, a story without an ending because it is still being written. Each new chip, each new factory, each new discovery adds another page. The chapters to come will be written by people not yet born, solving problems we have not yet encountered, creating technologies we have not yet dreamed. But all of it will trace back to this moment, this point in history when humanity learned to build thinking machines from sand. And so, as you drift into sleep, know that you are living in a remarkable time. A time when the impossible has become routine, when miracles are measured in nanometers, when the power of computation grows year after year without end in sight. The semiconductor chip, humble servant of our digital age, will continue its quiet revolution while you dream. It asks nothing in return but a little electricity and the chance to do what it was made for, to compute, to connect, to enable. Rest now, surrounded by the soft hum of technology, the glow of screens, the presence of billions upon billions of transistors working tirelessly on your behalf. They are the children of sand and lightning, of human genius and natural abundance. They are the building blocks of our connected world, and they will be there when you wake, ready to serve you once again. The story of the transistor is a story of persistence against seemingly impossible odds. When John Bardeen, Walter Brattain, and William Shockley began their work at Bell Labs, many scientists believed that solid-state amplifiers were theoretically impossible. The quantum mechanics of electrons in crystals was poorly understood, and previous attempts to build such devices had all failed. It took years of patient research, careful experimentation, and creative insight before the first working transistor emerged. Shockley, despite being part of the team that invented the point-contact transistor, was not present for the crucial breakthrough. He had been pursuing a different approach that was not working. When Bardeen and Brattain succeeded with their design, Shockley was determined to make his own contribution. Working intensively over the Christmas holiday of 1947, he invented the junction transistor, which proved more practical for manufacturing and became the basis for the semiconductor industry. The Nobel Prize in Physics for the invention of the transistor was awarded to all three men in 1956. By then, Shockley had left Bell Labs and founded his own company in what would become Silicon Valley. Though Shockley Semiconductor was not commercially successful, it proved enormously influential. When 8 of his employees left to found Fairchild Semiconductor in 1957, they started a chain of spin-offs that would create Intel, AMD, and dozens of other companies that defined the computer age. The region around Palo Alto, California, became known as Silicon Valley not because silicon was found there, but because so many semiconductor companies set up shop there. The name was coined by journalist Don Hoefler in a series of articles in 1971. At that time, the valley was transitioning from its previous identity as an agricultural region, famous for its apricot and prune orchards. Today, those orchards are long gone, replaced by office parks and fabs, and the headquarters of the most valuable companies in the world. The silicon used in chip making is not actually mined in Silicon Valley or anywhere in California. The purest silicon comes from special quartzite deposits, rocks formed from ancient sand that was compressed and heated deep in the earth over millions of years. These deposits can be found in various locations around the world, including Norway, Brazil, and Russia. The raw quartz is processed in steps that remove impurity after impurity until what remains is almost perfectly pure silicon. A typical silicon wafer goes through hundreds of individual processing steps during chip manufacturing. Each step must be performed with extreme precision, and any error can propagate through subsequent steps, ruining the entire wafer. The cumulative yield, the probability that a chip will work correctly after all these steps, is the product of the yields at each individual step. If each step has a 99% success rate and there are 500 steps, the cumulative yield would be less than 1%. This is why maintaining near-perfect success at each step is so critical. The chemicals used in chip manufacturing are among the most purified substances on Earth. The gases, liquids, and solids that come into contact with silicon wafers must be essentially free of any contamination. Even impurities at the parts per billion level can cause defects in chips. Producing these ultrapure materials is itself a sophisticated chemical industry, with specialized suppliers providing everything from ultrapure water to exotic gases like silane and phosphine. Photomasks, the stencils used to transfer circuit patterns onto silicon, are incredibly expensive and complex. A single mask set for a modern chip can cost several $1 million to produce. These masks are made from fused quartz covered with a thin layer of chrome, with the circuit pattern etched into the chrome with extreme precision. Any defect in a mask will be replicated on every chip made using that mask, so quality control is paramount. The scale of investment required for cutting-edge semiconductor manufacturing has created significant barriers to entry. In the 1980s, dozens of companies manufactured their own chips. Today, only 3 companies can produce the most advanced semiconductors: TSMC in Taiwan, Samsung in South Korea, and Intel in the United States. Even major technology companies like Apple, Google, and Amazon, despite their enormous resources, find it more practical to design chips and have someone else manufacture them. The concentration of advanced manufacturing in Taiwan has become a matter of geopolitical concern. TSMC manufactures chips for most of the world's major technology companies, and there is no easy way to replace this capacity. A disruption to TSMC's operations, whether from natural disaster, pandemic, or conflict, could have cascading effects throughout the global economy. This concern has driven efforts to build more chip manufacturing capacity in the United States, Europe, and other regions. The CHIPS and Science Act, signed into law in the United States in 2022, authorized nearly $53 billion in subsidies and tax credits to encourage domestic chip manufacturing. Similar efforts are underway in Europe, Japan, and other regions. These investments reflect a recognition that semiconductors are too important to rely on a few factories in a few countries. But building new fabs takes years, and training the skilled workforce needed to operate them takes even longer. The workforce required for semiconductor manufacturing is highly specialized. Fab workers need extensive training to operate the complex equipment and follow the exacting procedures required for chip production. Engineers must master multiple disciplines, from materials science to electrical engineering to computer science. The industry faces ongoing challenges in recruiting and training enough qualified workers, particularly as demand for chips continues to grow. Quality control in semiconductor manufacturing involves testing at multiple stages. Wafers are inspected after each critical processing step to identify defects early. Individual transistors are tested for electrical characteristics. Completed chips undergo functional testing to verify they operate correctly. Some chips are subjected to stress testing, running at high temperatures or voltages to identify units that might fail early. Only chips that pass all these tests are shipped to customers. The reliability of semiconductor chips is remarkable given their complexity. A typical processor contains billions of transistors that must all work correctly, billions of times per second, for years without failure. Modern chips are designed to operate for decades, far longer than the devices they are built into will typically be used. This reliability is achieved through careful design, rigorous testing, and continuous improvement in manufacturing processes. Heat management remains one of the biggest challenges in chip design. As transistors shrink and pack closer together, the heat they generate becomes increasingly concentrated. If not removed efficiently, this heat can cause chips to slow down, make errors, or be permanently damaged. Chip designers use various techniques to manage heat, including spreading hot spots across larger areas, reducing voltage and frequency when the chip is not fully utilized, and designing for efficient heat transfer to coolers. The cooling systems for high-performance chips have become increasingly sophisticated. Air cooling with heat sinks and fans was sufficient for early processors, but today's powerful chips often require liquid cooling or even more exotic approaches. Data centers, which contain thousands of chips operating continuously, face enormous cooling challenges. Some companies are experimenting with immersive cooling, where chips are submerged in special non-conductive liquids that carry heat away more efficiently than air. Power consumption is another critical concern, both for portable devices, where battery life matters, and for data centers, where electricity costs are significant. The industry has made tremendous progress in reducing power per computation. Today's chips perform far more calculations per watt than chips from even a few years ago. This improvement has enabled smartphones that can run all day on a single charge and data centers that can operate without consuming entire power plants. The environmental impact of semiconductor manufacturing extends beyond energy and water use. The industry uses numerous chemicals that must be handled carefully to prevent environmental contamination. Some of these chemicals are persistent pollutants that do not break down easily in the environment. Responsible manufacturers have invested heavily in waste treatment and pollution prevention, but the rapid growth of the industry continues to present environmental challenges. Recycling of electronic devices, including the semiconductor chips they contain, remains limited. While some materials like gold and copper can be recovered from circuit boards, most chip materials are lost when devices are discarded. The small size of chips and the complex mixture of materials they contain make recycling difficult and often uneconomical. As the volume of electronic waste continues to grow, finding better ways to recover and reuse semiconductor materials will become increasingly important. The speed at which the semiconductor industry moves is remarkable. A chip design that was cutting edge 3 years ago is now considered obsolete. Manufacturing processes that seemed impossible a decade ago are now routine. The industry has maintained this pace of innovation for more than 50 years, longer than most experts originally predicted was possible. While the pace of improvement has slowed in recent years, progress continues, and there is no clear end in sight. Looking back at the history of semiconductors, it is striking how many times experts predicted that progress would stop. In the 1960s, some thought chips could never have more than a few thousand transistors. In the 1970s, the limits of optical lithography seemed close. In the 1980s, quantum effects were expected to halt scaling. In the 1990s, heat problems appeared insurmountable. Each time, engineers found creative solutions and progress continued. The lesson seems to be that limits are often less absolute than they first appear. The future of semiconductors likely involves continued evolution rather than revolution. Traditional scaling will continue, though at a slower pace. New materials and architectures will provide additional improvements. Advanced packaging will enable new capabilities. AI will help optimize designs and manufacturing processes. Quantum computers may eventually handle certain specialized tasks. Neuromorphic and photonic computing may find their niches. The industry will continue to innovate, adapting to challenges as they arise. For most people, these technical details matter less than the capabilities they enable. What matters is that your phone can take better pictures, that your car is safer, that your doctor has better tools for diagnosis, that you can connect with loved ones anywhere in the world. These capabilities come from the endless progress of semiconductor technology, from the tireless work of scientists and engineers, from the transformation of sand into silicon, into circuits that improve our lives in countless ways. As sleep draws near, let your mind rest on these gentle thoughts of human achievement. The chips that surround you, in your phone and your lights and your thermostat and countless other devices, are working quietly through the night. They require no rest, no encouragement, no appreciation. They simply do what they were designed to do, computation after computation, second after second, year after year. They are humanity's tireless servants, asking nothing but a trickle of electricity, giving in return capabilities that would have seemed magical to our ancestors. The journey from sand to semiconductor is one of the great stories of human civilization. It involves physics and chemistry, engineering and manufacturing, economics and geopolitics. It spans continents and decades, requiring the collaboration of millions of people speaking hundreds of languages. It transforms the most common substance into the most complex creations, and it continues even now, in labs and fabs around the world, as researchers and engineers work to write the next chapter. Tomorrow, when you wake, the technology will be waiting. The chips will have kept working through the night, maintaining your devices, processing your data, keeping the world connected and running. They will be ready to serve you again, these tiny marvels that began their journey as grains of sand. And the story will continue, as it has continued for more than 70 years, into a future we can barely imagine. Sleep well now, in the quiet knowledge that human ingenuity has created wonders from the simplest ingredients. From beach sand to billion transistor chips, from primitive tubes to quantum computers, from room-sized machines to devices that fit in your pocket. The semiconductor story is still being written, and you are living in its most exciting chapters. Rest and let the chips do their work, these patient servants of our digital age, these children of silicon and light. The night is quiet, the technology hums softly, and tomorrow holds new possibilities. Sleep now, surrounded by the gentle presence of billions of transistors, each one a tiny switch turned on or off, together forming patterns of incredible complexity, enabling dreams we are only beginning to dream. The sand has become silicon, the silicon has become chips, and the chips have become the foundation of our modern world. Rest in this achievement, and let sleep carry you gently into morning. The semiconducting properties of certain materials were not always understood. For many years, scientists puzzled over why some substances conducted electricity well, others did not conduct at all, and a mysterious third category fell somewhere in between. The answer came from quantum mechanics, the strange physics that governs the behavior of atoms and electrons. In a semiconductor, electrons occupy energy levels that are arranged in bands. There is a gap between the filled bands, where electrons normally reside, and empty bands, where they could move freely if they had enough energy. In a conductor like copper, there is no gap between filled and empty bands, so electrons can flow freely with little encouragement. In an insulator like glass, the gap is so large that electrons cannot jump across it under normal conditions. In a semiconductor like silicon, the gap is just right, not too large and not too small. At low temperatures, semiconductors act like insulators. But as temperature rises, or when certain impurities are added, electrons can gain enough energy to jump the gap and conduct electricity. This property of semiconductors, having conductivity that can be controlled, is what makes them so useful for electronics. By carefully adding impurities to pure silicon, engineers can create regions that have extra electrons, called N-type material, or regions that are missing electrons, called P-type material. When N-type and P-type materials are placed together, interesting things happen at the junction between them. Current can flow easily in one direction but not the other. This is the basic principle behind diodes, transistors, and all semiconductor devices. The process of adding impurities to silicon is called doping. It must be performed with incredible precision. Too many impurities, and the semiconductor will not work correctly. Too few, and it will not have the desired electrical properties. The impurities are typically added by ion implantation, where atoms of elements like boron or phosphorus are accelerated to high speeds and shot into the silicon surface. The depth and concentration of the impurities can be precisely controlled by adjusting the energy and duration of the implantation. Each transistor on a modern chip is like a tiny faucet that can be turned on or off. When the transistor is on, current flows through it. When it is off, current does not flow. By combining millions or billions of these tiny switches in sophisticated patterns, engineers can create circuits that perform logical operations, store information, and carry out the computations that power our digital world. The basic logical operations performed by digital circuits are remarkably simple. An AND gate outputs a 1 only if both its inputs are 1. An OR gate outputs a 1 if either of its inputs is 1. A NOT gate inverts its input, turning 1 into 0 and 0 into 1. These simple operations, combined in vast numbers, can perform any computation that any computer can perform. This remarkable fact was proven mathematically long before practical computers existed. Memory circuits work differently from logic circuits. Instead of computing new results, they hold information over time. The most basic memory element is a flip-flop, which can be set to remember either a 0 or a 1 and will retain that value until it is changed. More sophisticated memory circuits include SRAM, which uses flip-flops and is very fast but requires continuous power, and DRAM, which stores information as tiny electrical charges and must be constantly refreshed but can pack much more storage into the same space. Flash memory, the type used in USB drives and solid-state drives, stores information in a different way. Each memory cell has a special structure called a floating gate, which is electrically isolated from its surroundings. Electrons can be forced onto or off of this floating gate by applying high voltages. Once placed, the electrons remain trapped, holding their information even when power is removed. This is why flash drives can retain your files even when unplugged. The transistors in different types of chips are optimized for different purposes. Logic transistors in processors need to switch very fast, so they are designed for speed. Memory transistors need to be small and reliable, so they are designed for density and retention. Power transistors in chargers and motor controllers need to handle high voltages and currents, so they are designed for robustness. This specialization means that modern electronics often contain chips made using many different manufacturing processes. The interconnections between transistors are as important as the transistors themselves. A modern processor might have 10 or more layers of metal wiring, with billions of connections linking billions of transistors. These wires must be as small as the transistors, just a few nanometers wide in places. They must carry electrical signals without too much loss and without interfering with neighboring wires. Designing and manufacturing these interconnections is one of the most challenging aspects of chip making. Copper replaced aluminum as the primary interconnect material in chips around the late 1990s. Copper has lower electrical resistance than aluminum, meaning signals can travel through it with less energy loss. But copper was much harder to work with because it tends to diffuse into silicon and ruin the transistors. Engineers had to develop new techniques, including lining all copper wires with thin barrier layers, before copper interconnects became practical. Signal integrity is a constant concern in chip design. As signals travel along wires, they can pick up noise from neighboring wires, a phenomenon called crosstalk. They can reflect off impedance mismatches, causing distortion. They can arrive at different times even when they started together, a problem called skew. Design engineers must carefully plan the routing of signals to minimize these effects, using sophisticated simulation tools to predict problems before chips are manufactured. Power distribution is equally challenging. Every transistor needs power to operate, and that power must be delivered through a network of wires that spans the entire chip. If the power delivery network has too much resistance, transistors far from the power sources will not receive enough voltage. If the network cannot respond quickly enough to changes in power demand, voltage droops can cause circuit malfunctions. Designing robust power delivery is essential for reliable chip operation. Clock signals coordinate the operation of digital circuits. Like a conductor keeping an orchestra in time, the clock signal tells all the transistors when to act. In a modern processor, this clock ticks billions of times per second. The clock signal must reach every part of the chip at nearly the same time, despite having to travel different distances to different locations. Clock distribution networks are carefully designed to minimize this clock skew. Temperature affects every aspect of chip behavior. Hot transistors switch more slowly and leak more current. Hot wires have higher resistance. Hot materials expand, potentially causing mechanical stress. Chip designers must ensure their designs work correctly across a wide range of temperatures, from the cold of a warehouse in winter to the heat inside a gaming laptop during intense use. They must also design for graceful degradation, allowing chips to slow down rather than fail when temperatures get too high. Electrostatic discharge, the same phenomenon that creates sparks when you touch a doorknob after walking across a carpet, is a constant enemy of semiconductor chips. The tiny transistors inside a chip can be destroyed by voltages of just a few volts, far less than the thousands of volts in a typical static spark. Chips include protection circuits at all their input and output pins to shunt away static discharges before they can reach sensitive internal circuits. Electromagnetic interference is another concern. The rapidly switching transistors inside a chip generate radio frequency signals that can interfere with other electronic equipment. At the same time, external radio signals can interfere with the operation of the chip. Careful design and shielding are needed to ensure chips neither emit too much interference nor are too susceptible to it. Regulatory agencies set strict limits on electromagnetic emissions from electronic devices. The testing of semiconductor chips is a science unto itself. Specialized machines called automatic test equipment can test chips at rates of thousands per hour, checking each chip against a comprehensive test program that exercises all its functions. Some tests are obvious, like verifying that a processor can add two numbers correctly. Others are more subtle, like measuring how much current a chip draws in various modes or how fast it can switch between states. Burn-in testing subjects chips to elevated temperatures and voltages for extended periods, weeding out chips that might fail early in their service life. This testing is based on the bathtub curve model of reliability, which observes that failure rates are highest at the beginning and end of a product's life, with a long period of low failure rates in between. By accelerating early failures during testing, manufacturers can ship chips that are past the high-risk infant mortality period. The yield of a semiconductor manufacturing process is the percentage of chips that work correctly after manufacturing. Yield is influenced by hundreds of factors, from the purity of input materials to the precision of processing equipment to the cleanliness of the manufacturing environment. Improving yield is a constant focus of semiconductor manufacturers because higher yields mean more working chips from each expensive wafer. Yield learning is the process of understanding and eliminating the causes of chip failures. Engineers analyze failed chips to identify patterns that point to specific processing problems. They adjust manufacturing parameters to eliminate these problems. They monitor ongoing production to catch any drift in conditions. This continuous improvement has pushed yields from the low percentages of early semiconductor manufacturing to the 90% and above that modern fabs achieve. The economics of semiconductor manufacturing are dominated by the enormous fixed costs of building and equipping fabs. A modern fab can cost $20 billion or more before it produces a single chip. This investment must be recovered through the sale of chips over the fab's productive life. High yields and high utilization are essential for profitability. A fab that sits idle for lack of orders or that produces too many defective chips will struggle to earn back its investment. The semiconductor industry has historically been highly cyclical. Demand for chips surges during economic expansions, and when new applications emerge, then falls during recessions. The long lead times for building new fabs mean that capacity often arrives just as demand is falling, leading to oversupply and falling prices. This boom and bust pattern has moderated somewhat as the industry has matured, but it remains a significant business challenge. Semiconductor companies use various business models to navigate this challenging industry. Integrated device manufacturers like Intel and Samsung design and manufacture their own chips. Foundries like TSMC manufacture chips designed by other companies. Fabless companies like NVIDIA and AMD design chips but outsource all manufacturing. Each model has advantages and disadvantages in terms of cost structure, flexibility, and access to cutting-edge technology. The relationship between chip designers and manufacturers has evolved over time. In the early days of the industry, the same engineers often designed chips and supervised their manufacture. As chips became more complex and manufacturing more specialized, these functions separated. Today, designers work with sophisticated software tools that model the manufacturing process, allowing them to create designs that will work in fabs they may never visit. Design for manufacturing is a discipline that bridges the gap between chip design and chip production. Design for manufacturing rules constrain designers to use only structures that can be reliably manufactured. Design for test rules ensure that finished chips can be thoroughly tested. Design for yield rules help maximize the number of working chips per wafer. Following these rules can be frustrating for designers, but it is essential for practical chip production. The software tools used for chip design, called electronic design automation or EDA tools, are themselves enormously complex programs. They include schematic capture tools for drawing circuit diagrams, logic synthesizers that convert high-level descriptions into transistor-level circuits, place and route tools that arrange transistors and draw the wires connecting them, and verification tools that check designs for errors. The EDA industry, led by companies like Cadence, Synopsys, and Mentor Graphics, is a critical enabler of semiconductor progress. Verification is often the most time-consuming part of chip design. A modern processor can have billions of transistors, far too many to check each one individually. Instead, verification engineers create test programs that exercise the chip's functions and check for correct behavior. They run simulations that model the chip's operation in software. They use formal verification techniques that mathematically prove certain properties of the design. Even with all these techniques, bugs sometimes escape into production, occasionally requiring costly chip recalls. The design of memory chips follows somewhat different principles than the design of logic chips. Memory chips consist of large arrays of identical cells, repeated millions or billions of times. The challenge is to make each cell as small as possible while maintaining reliability. Memory designers use specialized circuit techniques and aggressive scaling to pack maximum storage into minimum area. The result is that memory chips typically contain far more transistors per unit area than logic chips. Flash memory, the non-volatile storage used in solid-state drives, has evolved through multiple generations of technology. Early flash used planar transistors arranged in 2 dimensions. As those transistors approached their scaling limits, manufacturers moved to 3-dimensional structures, stacking multiple layers of memory cells on top of each other. Modern 3D NAND flash can have over 200 layers, packing enormous storage into a tiny space. The distinction between memory and storage is blurring as new technologies emerge. Storage-class memory technologies like Intel's Optane combine the persistence of storage with speeds approaching those of main memory. These technologies use different physical mechanisms than traditional silicon transistors, such as changes in the crystalline structure of special materials. While not yet widely adopted, they hint at the continued evolution of semiconductor technology. Specialized chips for artificial intelligence have become a major focus of semiconductor development. Training AI models requires enormous amounts of computation, particularly matrix multiplications and similar operations. Graphics processing units, originally designed for rendering video games, proved unexpectedly effective for AI training because they excel at parallel operations. NVIDIA's GPUs have become the workhorses of AI research, and the company's market value has soared accordingly. Companies are also developing chips specifically designed for AI inference, the process of using a trained model to make predictions. Inference typically requires less computation than training, but must be performed quickly and efficiently, often on devices with limited power. Apple's neural engine, Google's tensor processing unit, and numerous startup designs all target this market. The diversity of approaches reflects the uncertainty about which architectures will prove most effective. Quantum computing represents a fundamentally different approach to computation. Where classical computers process bits that can be either 0 or 1, quantum computers process qubits that can exist in superpositions of both states simultaneously. This property, combined with quantum entanglement, potentially allows quantum computers to solve certain problems exponentially faster than any classical computer. However, building practical quantum computers requires maintaining quantum states that are extremely fragile and easily disrupted. Various physical systems are being explored as qubits for quantum computers. Superconducting circuits, used by IBM and Google, are tiny loops of superconducting wire that can carry currents in both directions simultaneously. Trapped ions, used by IonQ and Honeywell, are individual atoms held in place by electric fields. Other approaches include photons, spin states in semiconductors, and topological qubits that store information in the collective behavior of many particles. Each approach has advantages and challenges, and it remains unclear which will prove most practical. The challenges facing quantum computing are formidable. Qubits must be isolated from any environmental disturbance that could collapse their quantum states, yet they must also be accessible for manipulation and measurement. Error rates in current quantum computers are far higher than in classical computers, requiring sophisticated error correction schemes that consume many physical qubits to create each reliable logical qubit. Despite enormous investments and rapid progress, practical quantum computers that outperform classical machines on useful problems remain largely aspirational. Neuromorphic computing takes inspiration from biological brains rather than quantum physics. The human brain is remarkably efficient at certain tasks, like pattern recognition, using only about 20 watts of power to perform feats that would require huge data centers using classical computing approaches. Neuromorphic chips attempt to mimic the brain's architecture, with artificial neurons connected by artificial synapses that can strengthen or weaken over time. Intel's Loihi chip is one example of a neuromorphic design. It contains about 130,000 artificial neurons connected by about 130 million artificial synapses. Unlike traditional chips that separate processing and memory, Loihi integrates them at the neuron level, similar to how biological neurons store and process information in the same structures. Applications for neuromorphic chips include efficient pattern recognition, robot control, and potentially much more as the technology matures. The speed of light itself becomes a concern in the largest chips. Light travels about 30 centimeters in 1 nanosecond, and a modern processor ticks more than once per nanosecond. This means that signals cannot travel more than a few centimeters during a single clock cycle. As chips grow larger to accommodate more transistors, this speed of light limit forces designers to organize their chips differently, using multiple processing cores and sophisticated communication networks rather than single large circuits. The future of semiconductors likely involves continued integration of different technologies on single packages. Advanced packaging techniques allow multiple chips, possibly made using different manufacturing processes, to be combined into single products. Memory can be stacked directly on top of processors. Specialized accelerators can sit alongside general-purpose cores. This heterogeneous integration offers a path forward as traditional transistor scaling becomes increasingly difficult. Materials research continues to explore alternatives to silicon. Carbon nanotubes have excellent electrical properties and can potentially enable smaller, faster transistors. Transition metal dichalcogenides are atomically thin materials that could enable even denser integration. Two-dimensional electron gases at the interfaces between certain materials exhibit strange and potentially useful quantum properties. While silicon will likely remain dominant for decades, these exotic materials may eventually find their niches. The manufacturing equipment used to make chips is itself a marvel of engineering. A modern EUV lithography machine from ASML contains hundreds of thousands of parts sourced from suppliers around the world. The light source alone involves lasers, tin droplet generators, plasma physics, and collection optics operating at the edge of what physics allows. The positioning systems can place wafers to within fractions of a nanometer. The computers controlling these machines run sophisticated algorithms optimized over decades of development. The supply chain for semiconductor manufacturing spans the globe. Silicon wafers might come from Japan or Germany. Specialty chemicals might come from the United States or Europe. Manufacturing equipment might come from the Netherlands, Japan, or the United States. The final chips might be made in Taiwan, South Korea, or increasingly in other locations. This global distribution of capability creates both efficiencies and vulnerabilities. Geopolitical tensions have elevated semiconductors from an obscure technical topic to a matter of national security. The United States has imposed restrictions on exporting advanced chip technology to China, seeking to slow that country's progress in artificial intelligence and military applications. China has responded with its own export controls on materials like gallium and germanium. These tensions have disrupted long-established supply chains and prompted massive investments in domestic chip manufacturing capacity. The environmental sustainability of the semiconductor industry is receiving increased attention. The enormous water consumption, energy use, and chemical waste associated with chip manufacturing are becoming concerns as the industry grows. Forward-thinking companies are investing in water recycling, renewable energy, and chemical recovery systems. Some are setting ambitious sustainability targets, aiming for carbon neutrality or even carbon negativity in coming decades. The skilled workers who design and manufacture chips are perhaps the industry's most valuable resource. Training a semiconductor engineer takes years of specialized education and experience. The knowledge of how to operate a fab is largely tacit, built up over decades of operation, and difficult to transfer to new facilities. As the industry expands into new regions, developing this human capital is often more challenging than building the physical facilities. Education in semiconductor technology spans from community colleges teaching fab technician skills to PhD programs developing next-generation researchers. Industry-academic partnerships provide students with hands-on experience and companies with access to cutting-edge research. Programs like the United States CHIPS Act include significant funding for workforce development, recognizing that people are as essential as equipment for semiconductor success. The history of semiconductors includes its share of dramatic failures as well as successes. Intel's Pentium floating point bug in 1994 required a costly recall when it was discovered that certain division operations produced incorrect results. Samsung's Galaxy Note 7 batteries, though not strictly semiconductors, illustrated how component failures can cascade through entire product lines. These failures, while painful, have driven the industry toward ever more rigorous quality control. Looking ahead, the semiconductor industry faces both challenges and opportunities. The traditional path of shrinking transistors is becoming increasingly difficult and expensive. But new architectures, new materials, new packaging techniques, and new applications continue to drive progress. The demand for computing power shows no signs of slowing, as artificial intelligence, autonomous vehicles, virtual reality, and other applications push the boundaries of what is possible. The chips that will power the devices of 20 years from now are being researched in laboratories today. Some of these research directions will prove fruitful, others will lead to dead ends. The particular technologies that will succeed are impossible to predict with certainty. What seems certain is that human ingenuity will continue to find ways to make computers smaller, faster, more efficient, and more capable, just as it has for the past 75 years. As you rest in the quiet night, these thoughts of silicon and circuits, of transistors and electrons, of human achievement and ongoing progress can accompany you toward peaceful sleep. The chips around you continue their silent work, processing, connecting, enabling. They ask nothing of you but will be there when you wake, ready to serve. They are the quiet servants of our age, descendants of sand and ingenuity, working through the darkness until morning light. Sleep well, knowing that somewhere in the world, engineers are solving problems that will make tomorrow's chips better than today's. Somewhere, researchers are exploring materials that might replace silicon in the distant future. Somewhere, fab workers are tending machines that run through the night, turning wafers into chips that will find their way into devices not yet imagined. The work continues, as it has continued for decades, as it will continue into futures we can only dream about. The story of semiconductors is far from over. New chapters are being written every day in laboratories and factories, in design studios and testing facilities around the world. The next breakthrough could come from anywhere. The next application could transform industries we have not yet considered. This is the nature of technological progress, unpredictable in its particulars, but remarkably consistent in its trajectory toward greater capability. And so we rest, in this moment of the long semiconductor story, surrounded by the fruits of decades of development, anticipating futures we cannot quite envision. The chips will keep working through the night. The research will continue. The industry will evolve. And when morning comes, this remarkable technology will be there, ready to help us face another day in our increasingly digital world. Good night and pleasant dreams of silicon and light. In the early morning hours, while most of the world sleeps, semiconductor fabs continue their work without pause. Robots glide silently through cleanrooms, moving wafers from machine to machine. Technicians monitor screens showing the status of hundreds of simultaneous processes. Quality control systems flag any deviation from specifications. The manufacture of chips never stops, a 24-hour operation that feeds the world's insatiable appetite for computing power. The wafers moving through these fabs each contain the potential for hundreds of individual chips. Each chip represents months of design work, billions of dollars of manufacturing infrastructure, and the accumulated knowledge of the entire semiconductor industry. By the time a wafer completes its journey through the fab, it has been photographed, etched, doped, deposited upon, polished, and inspected dozens of times. The transformation from blank silicon to functioning circuits is complete. The atoms in a silicon crystal arrange themselves in a pattern called the diamond cubic structure. Each silicon atom forms bonds with 4 neighboring atoms, creating a 3-dimensional lattice that extends throughout the crystal. This regular arrangement is what gives silicon its useful semiconductor properties. Any disruption to this perfect pattern, whether from impurity atoms or structural defects, changes the electrical behavior of the material. The band gap of silicon, the energy difference that electrons must overcome to conduct electricity, is about 1.1 electron volts. This value is particularly well suited for electronic applications. It is large enough that silicon does not conduct excessively at room temperature, but small enough that reasonable voltages can cause significant conduction. Other materials with different band gaps are used for different applications, such as gallium arsenide for high-frequency electronics and gallium nitride for power devices. Doping silicon with phosphorus adds extra electrons to the crystal structure. Phosphorus has 5 outer electrons, one more than silicon's 4. When phosphorus atoms substitute for silicon atoms in the crystal, that extra electron becomes loosely bound and can easily move through the material. This creates N-type silicon, where N stands for negative because electrons carry negative charge. Similarly, doping with boron, which has only 3 outer electrons, creates P-type silicon with mobile positive charge carriers called holes. The junction between P-type and N-type silicon is where the magic happens. When these materials are placed together, electrons from the N side diffuse into the P side, and holes from the P side diffuse into the N side. This creates a depletion region at the junction where mobile charges have been swept away. The depletion region acts as a barrier that allows current to flow easily in one direction, but blocks it in the other. This asymmetric current flow is the basis for diodes and the foundation of all semiconductor electronics. Transistors add a third terminal that can control the barrier height. In a field effect transistor, applying a voltage to the gate terminal attracts or repels charges in the channel between source and drain, either opening or closing the path for current flow. The beauty of this design is that very little current flows through the gate itself, so the transistor can be controlled with minimal power. This high input impedance is essential for building complex digital circuits. The oxide layer that insulates the gate from the channel is incredibly thin, just a few nanometers in modern transistors. Making this layer uniform and defect-free across billions of transistors is one of the great challenges of semiconductor manufacturing. Any weak spot in the oxide could allow current to leak through, causing the transistor to malfunction or fail entirely. The development of high-quality gate oxides was a major milestone in semiconductor history. As transistors shrink, the oxide layer must thin proportionally to maintain proper electrical behavior. But below about 2 nanometers, quantum tunneling allows electrons to pass directly through the oxide, causing unacceptable leakage current. This scaling barrier was overcome by switching to high-K dielectric materials that provide the same electrical properties with greater physical thickness. Hafnium oxide is now commonly used for this purpose, replacing the silicon dioxide that had been used for decades. The contact between metal wires and semiconductor material requires careful engineering. The interface between two different materials creates an energy barrier that can impede current flow. Certain metal semiconductor combinations create ohmic contacts where current flows easily in both directions. Others create Schottky contacts that act like diodes. Choosing the right materials and preparing the surfaces correctly ensures that contacts behave as intended. The tiny transistors in modern chips operate in a regime where quantum effects become significant. Electrons can tunnel through barriers that classical physics says should be impenetrable. Their positions and momenta cannot be simultaneously known with certainty. Their behavior is described by probability distributions rather than definite paths. Engineers have learned to work within these quantum constraints, designing circuits that function reliably despite the fundamental randomness at atomic scales. Statistical variation becomes increasingly important as transistors shrink. No two transistors are exactly alike, and with billions of them on a chip, some will inevitably differ significantly from the average. Designers must ensure their circuits work correctly across the full range of transistor characteristics that manufacturing variation produces. This requires sophisticated statistical modeling and design techniques that account for the randomness inherent in the manufacturing process. The testing of integrated circuits happens at multiple levels. Wafer sort testing checks each die while it is still part of the wafer, identifying and marking defective dice so they are not packaged. Final test checks packaged chips against their specifications. System-level test verifies that chips work correctly when installed in their target applications. Each level catches different types of defects and contributes to the overall quality of shipped products. Burn-in testing accelerates the aging of chips by operating them at elevated temperatures and voltages. Chips that would fail in the first few months of normal operation will fail within hours or days of burn-in. This screens out chips with latent defects that passed functional testing but would not survive long in the field. The cost of burn-in must be balanced against the cost of field failures, which includes not just the failed chip, but also the expense and inconvenience of repairs. The packaging of semiconductor chips has evolved from simple wire-bonded packages to sophisticated multi-chip modules. Early packages used gold wires to connect pads on the chip to leads on the package. Modern packages may use flip chip technology, where the chip is mounted face down with solder bumps making all connections simultaneously. Advanced packages can stack multiple chips vertically, include built-in capacitors for power delivery, and incorporate sophisticated heat-spreading structures. Thermal management starts at the package level. Heat generated by the chip must flow through the package to the outside world, where it can be removed by heat sinks, fans, or other cooling systems. The thermal resistance of the package, the difficulty heat has in flowing through it, is a critical specification. Low thermal resistance keeps the chip cooler, allowing higher performance or longer reliability. Advanced packages use materials like copper or diamond that conduct heat exceptionally well. The electromagnetic environment around a chip affects its operation in subtle ways. High-frequency signals can radiate from chip wiring and interfere with other circuits. External electromagnetic fields can couple into chip circuits and cause errors. Power supply noise can propagate through the chip and disrupt sensitive circuits. Managing these electromagnetic effects requires careful attention to chip layout, package design, and system architecture. Supply chain management for semiconductor manufacturing is extraordinarily complex. A modern fab requires thousands of different materials and components, sourced from hundreds of suppliers around the world. Any disruption to any supplier can halt production. The COVID-19 pandemic exposed these vulnerabilities when chip shortages cascaded through automotive and other industries. Building resilient supply chains has become a strategic priority for the industry. The environmental footprint of semiconductor manufacturing extends throughout the supply chain. Mining the materials, refining them to high purity, manufacturing the chemicals and gases, building and operating the equipment, all consume energy and resources. Life cycle assessments attempt to account for these full impacts, often finding that manufacturing dominates the environmental footprint of electronic devices despite the additional impacts of use and disposal. Recycling of semiconductor materials is technically possible but economically challenging. The tiny amounts of valuable materials in each chip, finely mixed with other substances, make extraction expensive. Some specialized recyclers can recover gold and other precious metals from electronic waste, but most semiconductor material ends up in landfills. Improving recycling rates will require both technological advances and policy support to make recovery economical. The social impacts of semiconductor technology are profound and ambiguous. Computers and smartphones have connected people across distances and enabled new forms of work and creativity. They have also created new forms of surveillance, addiction, and inequality. The same chips that enable life-saving medical devices also enable weapons of war. Technology itself is neutral, but its effects depend on how humans choose to use it. Privacy concerns have grown as chips enable ever more pervasive data collection. The sensors in smartphones can track location, activity, health, and more. Smart home devices can monitor conversations and habits. Connected vehicles know where you go and how you drive. The vast data generated by these chip-enabled devices raises fundamental questions about privacy, consent, and the boundaries between public and private life. Security vulnerabilities in chips can have far-reaching consequences. The Spectre and Meltdown vulnerabilities discovered in 2018 affected virtually every modern processor, allowing malicious software to access data it should not be able to see. Fixing these vulnerabilities required patches at the hardware, operating system, and application levels, with performance impacts that affected users worldwide. The incident highlighted how dependent we have become on the security of our chips. The concentration of chip manufacturing in a few companies and regions creates systemic risks. A natural disaster, pandemic, or conflict affecting Taiwan could disrupt the supply of advanced chips worldwide. Efforts to diversify manufacturing to other regions face enormous challenges in cost, expertise, and time. Building a semiconductor industry takes decades, and catching up to the leaders may take even longer. The workforce challenges facing the semiconductor industry are significant. The skills required for chip design and manufacturing take years to develop. Many experienced workers are approaching retirement. Competition for talented engineers is intense, particularly for those with expertise in cutting-edge technologies. Training programs at all levels, from technicians to researchers, are essential for the industry's continued success. Women and underrepresented minorities remain scarce in the semiconductor workforce, despite efforts to increase diversity. The industry's technical culture and demanding work schedules can be unwelcoming to those with caregiving responsibilities or different backgrounds. Broadening participation is not just a matter of fairness, but also of tapping the full pool of human talent that could contribute to semiconductor progress. The economic implications of semiconductor leadership are increasingly recognized by governments worldwide. Countries that lead in chip technology gain advantages in military capability, economic competitiveness, and technological independence. This recognition has driven massive government investments in domestic semiconductor industries, changing the dynamics of an industry that had long been driven primarily by commercial considerations. Standards play an important role in enabling the semiconductor ecosystem. Interface standards allow chips from different manufacturers to work together. Manufacturing process standards allow equipment from different suppliers to be combined in the same fab. Testing standards ensure chips are evaluated consistently regardless of who makes them. These standards are typically developed through industry consortia, where competitors collaborate on common technical foundations. The relationship between semiconductor progress and broader technological development is symbiotic. Advances in chips enable new applications, from artificial intelligence to virtual reality. These applications, in turn, drive demand for better chips, funding the research and development that enables further advances. This virtuous cycle has operated for decades and shows no sign of ending, despite the increasing difficulty of continued transistor scaling. The chips of the future may look very different from those of today. They may combine silicon with other materials. They may use light instead of or alongside electricity. They may exploit quantum effects deliberately rather than merely tolerating them. They may be manufactured in ways we have not yet imagined, using processes not yet invented. The only certainty is that human creativity will continue to find ways forward. As dawn approaches and the night draws to a close, these thoughts of technology and progress can fade into restful sleep. The chips will continue their work, marking time with billions of oscillations, processing data that represents the thoughts and activities of billions of people. They are the hidden infrastructure of modern life, as essential as electricity or water, as taken for granted as the air we breathe. The journey from sand to silicon to semiconductor to society is one of the great stories of human achievement. It involves physics at the quantum scale and economics at the global scale. It requires the collaboration of millions of people across dozens of countries. It transforms the mundane into the miraculous, turning beach sand into brains that can think, after a fashion, and certainly calculate far faster than any human. And so the night ends as it began, with you surrounded by the quiet presence of countless chips, each one a marvel of engineering, each one the product of decades of development, each one ready to serve you when morning comes. Rest peacefully in this technological abundance, this heritage of human ingenuity, this world of silicon and electrons, of photons and possibilities. The morning will bring new computations, new connections, new creations enabled by semiconductor technology. But for now, rest. Let the chips do their work while you sleep. They need no encouragement, no supervision, no thanks. They will be there when you wake, these patient servants of our digital age, ready to help you navigate another day in a world they have helped create. Sweet dreams, surrounded by billions of transistors, descendants of sand and genius, working silently through the night. Sleep well and wake refreshed to face a world of semiconductor wonders.